It's a pleasure and an honor, Ian, an audience, to be here and to be able to present our current research at the University of Barcelona. I left Cambridge 30 years ago, many years ago. Yeah, I'm a bit old. But I still try to apply lessons I learned in your group in our current research, and I'm sure you will be able to recognize your master hand behind many of the slides I'm going to present you. So thanks a lot, Ian. Thanks a lot. And I wish you from the very beginning all the best for the new stage you are going to start probably tomorrow. All the best to you, to Nina, obviously, all the members of the Paterson family. Okay, talking about chemistry. I'm going to present our carbon research, which deals with new approaches for the catalytic and enantioselective construction of carbon-carbon bond. And to put into context this research, probably it would be worth to tell you that for many years, our research revolved around the use of titanium enolates to stereoselective aldol, Michael, and Lewis acid-mediated additions to acetyl and glycols, and also the application of all these methods to the synthesis of natural products. 4 or 5 years ago, we slightly changed our mind, and let me say that, well, I'm going to tell you 2 stories in order to show what we are doing in our group. One of the stories stems from the synthesis of Herboxyden, and it talks about radical chemistry. Well, this is the molecule, Herboxyden. I'm not going to talk to you about the synthesis, but probably you recognize that there are 2 lactate ketones in the backbone of this molecule. Or it's probably much more easy to recognize these 2 aldol adducts that come from these ketones. Particularly, I'm talking about substrate-controlled titanium-mediated aldol reaction from lactate gate. The methods were well established in our group, and we had access to anti-syn and syn-syn adducts with an excellent diester selectivity. However, not from an experimental point of view, but from a mechanistic point of view, we have some concern. These concerns dealt with the real structure of the enolate. Probably it could be a normal enolate, or probably an innate enolate in which titanium has an octahedral coordination. It was important for us because we wanted to develop new approaches, but we couldn't find experimental proof for enolate or 8 enolate. So what we did is ask for help, and we asked 2 of our colleagues working in the department, working on computational chemistry, if they could try to work out what kind of a structure was the most important. We thought it was the 8 enolate, but we needed much more support. Well, they started working, and a few weeks later, they knocked on my door, they came into my office and told me, okay, you were right, the most important species is the 8 enolate, but be careful. There is another species, which is a biradical, in equilibrium between with this enolate. I didn't understand at all, because you know how computational chemists talk, no? I'm sorry. I'm sorry. Well, I'll try to explain you what I learned. Basically, sorry. Look, this, like this titanium oxygen. Well, depending on the distance of this titanium oxygen bond, you can have the classical, closed shell. This is the right line here. More or less, the configuration, electronic configuration is here. But for some reason that I didn't understand, when this distance becomes longer, from this point, then an open, electronically open shell becomes much more stable. So it means that you really have an equilibrium between 2 electronical configuration, which is named balanced autonomy. We were very happy because we felt like Janus God. Janus God was one of the most important gods in Roman times, all times, and probably you know that January, the first month of the calendar, stands for Janus. And Janus is represented by this got with two phases. One of the phases look at the past. For us, was the nucleophilic compounds or nucleophilic chemistry, and the other phase looks to the future. And for us, it was radical chemistry. And we started that trip. It was not easy. It was hard. We had to work hard. But finally, we were able to prove that this chemistry worked, in particular starting from this compound and treating this compound with titanium chloride under standard conditions and adding tempo. Then we were able to construct these oxidized compounds with an excellent diester selectivity. In order to understand the mechanism, it's very easy. You can imagine the synthesis of the rigid chelated titanium enolate with titanium in an octahedral geometry. Now it's in equilibrium with the biradical counterpart, and then this biradical can react with one molecule of tempo. Then you get the corresponding oxidized compound, and then a second molecule of tempo oxidize the titanium 3 to titanium 4, and when you quench the reaction, you get the compound you see here. Obviously, we were very happy, and we started working on the application of this system. As you can see, the method is highly selective, highly diester selective with high yields and mild conditions. So it worked. But we were not happy enough, and we started looking for another sources of radical. And as you can imagine, diacyl peroxide was our options because the oxygen-oxygen bond is very weak. And then we thought that probably in the reaction mixture, these peroxides could break into two radicals, and then we could take advantage of the radical chemistry. At that moment, we had in the lab two peroxides. One is BPO and the other is LPO. BPO is the dibenzoyl peroxide, and it works as expected, and we got the corresponding oxygenated product. LPO is a bit different, and it was a surprise for us because we observed the synthesis not of the carbon-oxygen, but the carbon-carbon bond. It's a standard C alkylation. So it was a surprise to us, and we decided to go in this direction. At that time, one of our PhD students, Marina, joined the group, and she took the management of this project, and she was able to develop a new approach for the C-alpha alkylation of titanium enolates using diacyl peroxide. In order to understand the mechanism, I asked also for help one of our colleagues from the University of País Vasco in the north of Spain, and he was able to account for the stereochemistry observed, imagining that the diacyl peroxide approaches to the titanium enolate for the other side of the benzyl group, and then taking advantage of the biradical 4, this approach produces a single electron transfer from the enolate to the diacyl peroxide. The enolate becomes a real radical, and then the peroxide becomes an anion, a radical anion. It's very stable and immediately decomposes in carboxylate, CO2, and radical, and then coupling of both radicals produce the carbon-carbon bond. And when you quench the reaction, in the case of lauryl LPO, we observe just a single diastereomer with a 93% yield. Okay? It's very general. The method is highly chemoselective, diester selective with high yields under mild conditions. Unfortunately, it only works for primary or secondary groups. It's important because it's not easy to introduce isopropyls or groups like cyclopentyl, cyclohexyls in other case, in the alpha position, but we wanted more. And unfortunately, when we try to apply this method to other system in order to introduce tertiary groups, we fail because the peroxides from this aliphatic acid are unstable, and we couldn't use it. So Marina changed again. She explored other reagents, and she found that terbutyl-perester are less reactive. They will work. And then she was able to introduce secondary and tertiary groups with excellent results, as you can see. So, more or less, the summary of this part is you can introduce primary, secondary, or tertiary groups. It doesn't matter. For primary and secondary, you have to use diacyl peroxide, and for secondary and tertiary, you can have to use terbutyl peresters. But it's good, it works, no? We have applied this chemistry to the synthesis of ligands for asymmetric synthesis, and also we have used it for the synthesis of a natural product that we have recently submitted for publication. Okay, Marina is very proud, and she thought, okay, this chemistry works. We have applied or transport this chemistry to the construction of carbon-carbon bond, but there are some challenges to be met. Particularly, she was interested in exploring other transition metals, and especially under catalytic premises and also in an enantioselective form. So basically, she was looking for a direct catalytic and enantioselective transformation. She was about to finish her PhD. Actually, she is going to pass her Viva probably in 1 month or 1 month and a half. But the question remains. I mean, titanium work, titanium-3, titanium-4, but the question was, could we apply the same chemistry to chromium, iron, cobalt, nickel, and copper? And particularly, she was interested in this reaction. TEMPO was a probe, is a starting material to examine all this reaction. But now we are especially interested in using any salt from any metal in the transition, the transition metal, but using catalytic amounts. So Marina finished in October, November, her experimental part, and Eduard joined the group in January. So in the last months, we are very happy because we have been able to prove that this chemistry can be exported to copper using a 10% of copper acetate and adding phenanthrene, working in cetronitrile at 30 degrees for 24 hours. We're able to isolate these compounds in 95%. It's very simple. It's very easy. And we imagine our working hypothesis is that obviously copper salt make enolate. This is an equilibrium between copper 2 and copper 1, a biradical. This biradical can react with TEMPO. We make now bonds. It's copper 1. Copper 1 is again oxidized with another molecule of TEMPO. And finally, we got the compound. It's released, and we recovered copper 2 to start another cycle. So now we are more or less in this situation, and we are very excited because I think we feel quite confident that probably in the next months we will be able to report interesting results about this kind of chemistry, and particularly with the emphasis on catalysis. Okay? So talking about catalysis, this is the same story I told you at the beginning of my talk. The second story deals with the synthesis of pelorusite and is based on catalysis. Well, actually, we were interested in the synthesis of C9, C19 fragment of pelorusite A, and particularly with the installation of these 4 steel centers. And we chose this molecule because we had a method based on titanium chemistry to install the stereocenters C13, 15, 18. And finally, we thought that the last one, the C11, could be introduced by using substrate control Mukayama alkyl-aldol reaction. Okay, we succeeded. We published this. But later, we noticed, okay, we are using 3 key reactions based on open transition states. So we could try something new. And what's new? Well, the challenge is to be met is a common approach for all the reaction, and particularly for direct catalytic and enantioselective reactions. So basically, the idea is if you keep in mind the intermediates, electrophilic intermediate and the former reaction, we have all these. The first one came from methyl orthoformate, the second one from acetal, yeah. The third one was the acylation of an aldehyde, the fourth, the Michael, fifth, the alkylation. So probably we could find good solution for all this stuff and summarize all these reactions in a single model. We start working with titanium, and honestly speaking, with a completely disaster. We didn't succeed a lot. So we were about to give up the project, but then 2 articles came into our help. One was due to Dave Evans. He published in JACS in 2005 this approach in which, using a very similar system to us, he was able to react with methyl orthoformate activated by boron trifluoride in the presence of a chiral nickel complex. Unfortunately, this chiral nickel complex is very difficult to manage. I mean, it must be prepared in a glove box. You have to take very strict conditions. And actually, if you have a look to the literature, you will notice that there are few papers dealing with this nice chemistry. So, however, 2 years later, Mikiko Sodeoka published in Angewandte similar, well, in some way, similar paper using, look, the same complex, but now it's not a triflate, now it's a dichloride. Dichloride is a very robust complex, it's not a problem, you can handle with a problem, and this nickel dichloride can be activated in situ by adding just test triflate. Obviously, she used this chemistry to introduce fluorine, but we think, okay, probably if we move from titanium to nickel, we have some chances to get the message. And we did it. And Stuart Kennington, a chemist from Warwick, joined the group. He was the head of the project, and he was able to prove that working with this substrate here, a 6-member sulfur-sulfur scaffold, this one here, then, and using the complex, the nickel complex here from DTBM6-phos, and activating the complex using test triflate, then he was able to produce the corresponding adducts in very good yield and with very good results. Particularly, the electrophilic scope was from orthoformate, diaryl ketones, benzyl ketones, and tropylium. And he was able to get an excellent control on the configuration of the alpha stereocenter. He applied here, more or less the summary of the method can be shown in this spot. We submitted an organic synthesis, it was approved, and it was checked, and it was published at the beginning of this year. And basically, you can see that we can build a carbon-carbon bond with an excellent steric control on the alpha stereocenter, and with an excellent chemoselectivity. Okay? More or less, the idea, and this is the model reaction, is that while the use of test triflate is twofold, the first step is used to activate the nickel, sorry, it's a mistake, it's the beginning is a nickel chloride. It's converted into the reaction mixer into the corresponding nickel triflate, and also the test triflate also prepare the corresponding electrophile. So basically the idea is, okay, the nickel triflate is an excellent Lewis acid, can coordinate with the lutein. You remove the alpha proton, you can get now the nucleophile. The nucleophile reacts with the carbanium ion, and through an open transition stain, we get the new carbon-carbon bond, and now it's released, and we get again the nickel triflate. And this history starts again. So we were very happy, and Stuart thought, okay, this chemistry work with electrophiles from orthoformate and also from ketal, so they are structurally similar. What about this aldehyde? If we can activate the aldehyde with a silicon, I hit it, and we obtain an antiprotective aldol just by mixing the starting material you see here in the present. Now it's not a TDTBM secphos, but it's toluene binap using TIPS triflate as activator. As you can see, it can be applied to a large number, a wide variety of aldehydes. The method in general is highly chemoselective, diastereoselective, with an excellent enantioselectivity, and just using a teeny amount of the catalyst, almost good to high yields. And it was very happy. We were very happy because another PhD student, Saul Teloxa from Mexico, was able to apply this chemistry to a special kind with the alpha position and a side, and also instead of sulfur-sulfur 6-member, sulfur-sulfur 5-member scaffold, but the reaction worked pretty well. Almost one diastereomer, almost one enantiomer with excellent yield. And also it's important to highlight that these scaffolds can be removed very easily. So the addition to the reaction mixture of an alpha amino acid makes the corresponding dipeptide in just a single step. And obviously, manipulation of the acido group allow us to synthesize many tripeptide fragments completely protected. More or less, we have submitted a paper, it was approved, and now is in press. And we try to show and to prove in this paper that it's very easy to get all these fragments in a few steps in an excellent steric control and yield. Okay, the chemistry worked, but as you well know, we always dream that it can be applied to many systems. And the idea was to use dialkane acetyls. Mikel and Elise Romero and in this project, and they found that when we changed the former scaffold to a sulfur oxygen scaffold and we recovered DTM secphos using dialkyl acetal source of electrophiles, now we obtain not the anti, the same protecting aldol. So preliminary results are here. You can use dimethyl, dibenzyl, or diallyl acetals. You can see that we only obtain one enantiomer, 99 EE, with excellent yields, and there is the selectivity, and it can also be applied to many other systems. And finally, we wonder, okay, we have been working with aromatic aldehydes. What happened with alpha beta and saturated aldehyde? Oriol made the challenge, and challenge now means that we are looking for a chemoselective method, obviously a stereoselective, diasterol and enantioselective, but alpha beta and saturated aldehydes puts another challenge, which is radioselectivity between aldol and Michael. Preliminary results here prove that using the same scaffold, sulfur oxygen 6-member, we can get the corresponding aldol, no problem, using TMS triplet as activator. But when we move to another scaffold, another activator, sulfur-sulfur and TIPS triplet, now we move from aldol to Michael, and only Michael reaction with a diacetyl higher than 9 to 1. And particularly important, yeah, last slide. We can get the syn Michael, and changing the catalyst, we have also access to anti-Michael. So this is the summary. I mean, chemistry works pretty well. We can get all the stereoisomers we want, and we hope we can finish all this area and publish as soon as possible. Okay, more or less the summary is working with different scaffolds, adding different ligands, and working nickel and copper on different activators, TMS or TIPS triplet. We can get direct catalytic and enantioselective transformation, and this is thanks to the people. This is another kind of lab we have. It's a tapas bar in Barcelona. This is a picture we took at the outside, and also having a typical meal. All these students are very hard working, and well, they are the responsibles of the chemistry I have just spoken. So thank you very much for your attention.